Hi everyone. This series of videos is going to take you through lesson 7B in the new packet, which is pages 4 and 5. If you haven't already, I do suggest that you print pages 4 and 5 if you have access to a printer, or if nothing else, have page 4 and 5 open on some sort of screen, maybe a new tab or something like that, so that you can follow along with the problems while you're working on a separate piece of paper. In any case, this lesson is going to introduce you to a new notation for sequences called recursive notation. The notation you were using in the previous set of lessons on pages 2 and 3 was called explicit notation. So all of those notes that we made together about things regarding arithmetic sequences and geometric sequences, those equations that we were dealing with, specifically the ones that looked like the ones on page 3, are called explicit equations. And an explicit equation generally does a really good job of telling us the two things that we need the most in an equation for a sequence. It tells us where to start, we call that the initial value, and it tells us what to either multiply or add by in order to keep generating subsequent terms. So explicit equations are super helpful and always have a very predictable format, which is really great. The new notation that we're going to learn, recursive notation, is just a slightly different way of communicating the same information. Notation as a word just means the way we write something. So recursive notation is just going to be a new way of writing equations, although it's not going to change what we fundamentally know about a sequence itself. For example, if we take a look at question number 1, we can see a sequence with a pretty distinctive arithmetic pattern. -8, -2, 4, 10, that's clearly going to be adding 6. So it must be arithmetic. And the idea is, if I know that this is an arithmetic pattern, that I could be able to write an explicit equation for it. But in letter A, it's not quite asking me to do that yet. Instead, it's asking me to find two different ways of figuring out the 10th term. Now, if I look at this information, it might be a little bit unclear which term they're talking about. So sometimes I like to organize sequence information in tables rather than in a list, because I do think a table can be a slightly more helpful way of organizing this info. Sequence tables are always in terms of n and t of n, not x and y. So if you're making a table for yourself, consider kind of doing the same thing. Now, as I look at the terms, I have to remember that when I see a list of terms, the first number in the list is quite literally the first term in the sequence, where n is 1. So the first term is -8. The second term is -2. The third term is 4. The fourth term is 10, and so on and so forth. So just remember that n is essentially like the term number. It's kind of like saying where you are in the sequence. You're in the first spot, you're in the second spot, you're in the third spot, you're in the fourth spot. And t of n is the actual value of the term itself. T of n is the actual number in those spots. Now, this is going to task me with finding the 10th term. So off the top of my head, I can definitely think of a couple of different methods, and hopefully you've done the same. So take about 20 seconds for yourself to kind of look at this table and to ask yourself, if you had to go all the way down to the 10th term, what could you do to figure out the value that goes in that t of n spot? Take a few seconds to brainstorm and think, and then I'll share with you my ideas and you can see how well yours lined up. Take a few more seconds to think. Okay, so off the top of my head, here's what I theoretically could do. One option, sounds tedious, but I could do it, is to basically fill in all of the missing values in the table between the 4th and the 10th term. So if, for example, I grabbed a piece of scratch paper and maybe extended my table, maybe made a longer one, the 4th term was 10, I could theoretically just keep building more tables. So the 5th term, 6th term, 7th term, 8th term, 9th term, and finally 10th term. And I could say to myself, okay, well, if the pattern is adding 6, then I could just keep going. 10 plus 6 is 16, plus 6 is 22, plus 6 is 28, plus 6 is 34, plus 6 is 40, plus 6 is 46. So it looks like the term, or the 10th term, should be 46. Now, fortunately, that was a relatively easy pattern, but that was a little tedious. I mean, I didn't need all these numbers in between. I just needed to write them down so I could keep track of where I was in the sequence. Now, the other option, perhaps a more appealing option to those of us who like to think more efficiently, is to consider using an equation. I could write an equation for this sequence using what I know from the previous lesson. If the initial value is the 0 term, and I can do an adder with n, then I can kind of fill in that template, so to speak, that we used in the previous lesson, and I could definitely figure out an explicit equation here. I just need to specify what the initial value and what the adder are supposed to be. So if I look back at my table, I know that the initial value is supposed to be the 0 term. So if I think about this pattern, it's adding 6 to go forward, but to go backwards to the 0 term, I'd need to subtract 6. I can do that by calling the 0 term negative 14. I'll just work backwards one step and assume that must have been the initial value. Now, since I was adding 6, I know that my equation is going to say plus 6n in terms of its structure. So there's my equation that I can use. T of n equals negative 14 plus 6n. But now, perhaps most importantly, I can say to myself, wait a minute, I want the 10th term. That means 10 is the term number that I want. Well, we already specified that n is the term number. So if I want the 10th term, that means I could definitely just plug in 10 for n, and I can, quote unquote, do the math. Now, if I plug in 10 for n, that becomes negative 14 plus 6 times 10 is 60, and negative 14 plus 60 is, not surprisingly, 46. The same 46 that I got when I actually just kept counting and counting and counting until I got to the 10th term. So those are two different ways I could have found the 10th term. They both obviously have their pros and cons. The upside to just extending the table is it's pretty easy. I mean, just adding 6 a bunch of times, definitely not that difficult from a mathematical standpoint. The upside to writing an equation is that it was very efficient. I didn't have to do the 4th, the 5th, the 6th, the 7th, the 8th, and the 9th terms that I didn't even need. I just needed one single initial value, which I could easily find in one step, and the structure of the equation, which I already know. So in theory, both ways have good and potentially drawback type approaches, and you'll just kind of want to keep that in mind in terms of the difference between counting, which is easy but tedious, and equations, which requires you to know a little bit more, but certainly is a bit more direct. Now that said, I've kind of given myself an advantage for letter B, because letter B says write an explicit equation, and that's actually what I did as the second method that I was describing for part A. This is the explicit equation that I wrote in order to plug in and evaluate. So I'm just going to transfer the work that I've already done for my explicit equation into my answer space. T of n equals negative 14 plus 6n, because I know that's correct. Now, underneath, it's asking me to put words to something that, to be honest, I don't normally think about. It says, what does n represent? What does T of n represent? And that might be a little bit misleading because we're like, wait, what? Like, what? It's just what we write. But let's use the table to help suss out what we'll write for these questions. Where it says, what does n represent? Let's go back to that conversation we had earlier in this video about what exactly n was in this labeling scheme. When n was 0, that was referring to the 0 term, or the initial value. When n was 1, that was referring to the first term. When n was 2, that was referring to the second term. So n, to reiterate, is still the term number that you're referring to in a sequence. So if you're referring to n equals 2, you're talking about the second term. If you're referring to n equals 4, you're talking about the fourth term. Now, t of n is the actual value in the sequence. If I say n equals 4, that's just telling me to look at the fourth spot in the sequence. But the actual value in that fourth spot is 10. So t of n is the actual value of the term, the actual 10, so to speak. You can almost think of it, if you want to, as n being kind of like a counter. N is telling you where you are in the sequence, and t of n is the important part. T of n is the part that tells you the actual number in that spot. So it's almost kind of like n is telling you which spot you're in, but t of n is telling you what's there. Now, generally then, think of that idea that n is where you are in the sequence. And take a look at this next expression, t of n plus 1. T of n plus 1 is interesting because all of a sudden there's a plus 1 inside of those parentheses. But instead of focusing on the t, let's just focus on the n plus 1. And let's think about this for a second in the context of what we already know. Let's focus on a term that we already know. Let's say n equals 3. If I was at n equals 3 in my table, n plus 1 is making me think of 3 plus 1. Well, that's just 4. So if I'm at n equals 3 and 3 plus 1 is 4, then this expression says t of 4. Well, that's just the next term. So what if n is 4? If I was thinking, well, n is 4 then. 4 plus 1 would be 5, t of 5. Oh, that's just the fifth term. So n plus 1 is actually just kind of saying, okay, well, here you are at n plus 1 is simply the next term in the sequence, the next term to the right, if you want to think of it in those terms. So n plus 1 is really just the term after the one you're given. And I'm writing this, but hopefully you can rephrase this if you need to put it in your own words. If you're given n equals 2, n plus 1 is term 3. If you're given n equals 10, n plus 1 is term 11. So n plus 1 just means the next one. Think of n plus 1 as meaning next, if you want to think of it in that phrasing. Now in letter D it says write an equation that could represent t of n plus 1. And that's where things get a little bit interesting, because to think about it, I actually think this table might come in handy. Let's say for a moment n is 10, because that's the last spot in the table that I actually knew something about. N is 10, and that's where I stopped. So let's think. If I have t of n plus 1, 10 plus 1 is 11, think about how you'd get the 11th term. If I was keeping this table going, I would simply take whatever was in the 10th spot and add 6 more. In other words, I would take whatever was in the 10th spot or whatever was in the t of n spot, and I would simply add 6 more. And if I wanted to keep going, the same thing would happen again. If now n is 11, and I want to get to n 12, that again is n plus 1, so that again is like another jump in the table, I would simply take whatever's in the t of n spot and add 6 more. So in theory, all we're doing to get to the next spot in the table is taking whatever's in the previous t of n space and adding 6, and that quite literally is the t of n plus 1 equation. So what they're actually looking for here is t of n plus 1 equals, so it said write an equation that could represent t of n plus 1, so we write t of n plus 1 equals t of n, which is what we already had in theory, whatever was in that bottom space, plus 6 more, because that's what the pattern is going to be. Now you can always check your equation to make sure it works. You can think of it almost like an actual algebraic substitution. Let's check a value that we know for sure we're really sure about. Like for example, let's check this pair of numbers, the 5 and the 16. Let's check that one because we know that. We knew that already. We knew that the pattern was good there. So if t of 5, because n is going to be 5, plus 1, equals t of n, that's going to be the bottom row, so that's 16 plus 6. Now I'm going to simplify what I wrote. T of 5 plus 1 is 6, and 16 plus 6 is 22. Oh, hey, that is correct. T of 6, the sixth term, is 22. I can see it in my table. It totally works. So that's how you can tell that this equation actually is valid. If you plug in any set of numbers from the sequence into n and t of n, you will be able to verify that your equation works. This, in part, is called a recursive equation, or a recursive definition. A recursive definition has kind of a telltale structure. It starts with t of n plus 1. And instead of n as the variable on the other side, it actually uses t of n as a variable of sorts. If that's confusing to you, don't worry about it too much. For now, though, what I'm going to ask you to do is to think about and try to suss out the structure in number 2. In number 2, it's giving you another recursive equation, very similar to the one we wrote in number 1, but obviously this one has a minus 3 instead of a plus 6. Similar structure, different value. It wants you to show or explain how this equation can be used to represent a new sequence. So notice a new sequence of values where the first term is 10, second term is 7, third term is 4, fourth term is 1. My suggestion is make a table, kind of like you saw I did in my scratch work for number 1, and see if you can make some sense of how that equation fits this sequence of values. Between now and the time that you begin the next video, try question number 2. Also, if you want to validate it, you can check your answer using the answer key, because I provided one example of how I verified that this equation matches up with this sequence. And you can certainly use mine as a bit of inspiration. In the next video, we'll begin question number 3. So between now and the time you start the next video, do question number 2, check your answer, and take some time to digest the information. Make sure everything makes sense before you start working on question number 3.